Bismillahirrahmanirrahim. Today the topic is about multiplication and division. For multiplication, normally we use two shortcodes, IMUL and MUL. IMUL is used for signed multiplication and MUL is used for unsigned multiplication. Signed means a number with plus or minus sign. These are some of the examples related to multiplication. Like MUL CL represents AL is multiplied by the value of AL is multiplied by value of CL and the unsigned product is saved in AX. It means here A register A is used by default. As you know that the result of product will be larger, that's why larger register is used here, that is AX. Here is an example ready to code. We need to multiply two numbers 5 and 10. So first we remove the value 5 in BL register and then remove the value in CL register. Then we position the data in AL, that is by default used for multiplication operation. So move AL, CL, the value 10 is moved in AL. Then in order to multiply we will use mul space BL. Now automatically 10 will be multiplied with the value in BL register, that is 5, and the result will be stored automatically in AX register. Now if we want to save the result in DX, then we will move the result from AX to DX. So the code will be move DX, X. This way final result will be stored in DX register. For 16-bit multiplication, the main difference is that AX contains multiplicand instead of AL. Now the 32-bit product appears in DX, AX. Two registers are used here, DX and AX, instead of only AX, because we need to save 32-bit information. So here are some examples related to 16-bit multiplication. AX is multiplied with CX and the 32-bit product will be saved in DX, AX. Higher 16 bits saved in DX and lower 16 bits are saved in AX. In the same way, I mul DI, again AX multiplied by DI, the product is saved in DX, AX. Higher bits in DX and lower bits in AX. For 32-bit multiplication, we need to use extended registers, because the product of 32-bit numbers will be a 64-bit number. So extended bit registers are used in this case. Here are some examples. Mul ECX. Now EAX is automatically multiplied by ECX and the product is saved in EDX, EAX. So higher 32 bits are saved in EDX and lower 32 bits are saved in EAX. The same way for 64-bit multiplication, R registers are used. The product will be 128-bit number. So as you can see in this case, small RCX. So the value in REX is multiplied by RCX and the unsigned product is saved in RDX dash REX. So higher 64 bits are saved in RDX and lower 64 bits are saved in RAX. Next is division operation. Again we use IDiv for signed division and div for unsigned division operation. Now 8-bit division use the X register to store the dividend that is divided by the contents of any 8-bit register or respective memory location. Now let's see an example. So this table tells us that div CL means AX is automatically used in division operation. AX is divided by CL. The value in AX is divided by CL register, and the unsigned quotient is in AL, and the unsigned remainder is saved in AH. So quotient will be saved in AL and the remainder will be saved in AH. In the same way, signed division. So AX is divided by BL. The signed quotient is in AL and the signed remainder is in AH. So this is an example related to division operation. Here a number is saved in num location. First we move num in AL and move 0 in AH in order to place 0 value in AH register. Now a specific value is already present in AL. Now div number 1, it means the value in AX register or AL register is divided by value in num1 location. Now division will be performed and the quotient will be in AL register and the remainder will be in AH register. Now we are moving the quotient value in a separate memory location named as ANS. Answer Q stands for quotient. We are moving the value of quotient in this location, and the remainder in AH is moved in ANSR. ANSR means ANS answer and R stands for remainder. Now again for 16-bit division operation, except that in dividing into AX, the 16-bit number is divided into DX, AX. Here we use DX and AX registers. Here in this example, the task is to, if a 16-bit unsigned number is placed in AX, DX must be cleared to 0. But in 8086 and above, the number is 0 extended by using move ZX instruction if AX is 16-bit number, then CWD command instruction sign extends it into a 32-bit number. So CWD command will be used for higher processors. Like these two numbers, the assigned numbers, -100 is moved in AX and 9 is in CX. Now for sign extension, we use only CWD. It will extend word into double word, that is 32-bit. Next is automatically divide I div CX. So the value is -100 is divided by 9. For 32-bit division, again extended version is used, EDX and EAX, and the rule for conversion will be CDQ. That means convert double word into quad word. Quad word means 64 bit. So 16-bit division. Now DCX means DXAX are used is divided by the value in CX, and the unsigned quotient is moved in lower half, that is AX, and the unsigned remainder is moved in higher half, that is DX. The same way for sign number, TXAX is divided by SI. Signed quotient is saved in EX and the signed remainder is saved in DX. So these are 32-bit instructions. Now for ECX, we will use extended register DX and AX. EDX, EAX is divided by ECX and the unsigned quotient is moved in EX and unsigned remainder is moved in EDX. So here is a code that tells division. Div BL automatically number in AX is divided by BL, then double remainder, add AH in AH. It means same value is added. Now test for rounding, that is by comparing. CMP stands for comparing. So BL is compared with the value in AH. Jump below. If it is okay, then it will move next. Otherwise, it will increment here. And again, AL is divided by BL. It will continue until jump below occurs. For next, it will move for next. It will move towards some next instruction. For this problem, we have two values. 13 is divided by 2. Now we are loading 13 in AX and 2 in BX by using move instruction. Then div BL automatically divides 13 by value in BL2. Then again we are moving the quotient from AL in ANSQ and we are clearing AL register. Then again div BL. It will generate the again div BL, it will generate the remainder. So the value generated in AL is moved towards the location toward ANSR. For 64-bit division, R, R registers are used like div RCX. For div RCX we used RDX and RAX combination. It is divided by RCX and the unsigned quotient is moved in REX and unsigned remainder is moved in RDX. So this is all about multiplication and division.